what question do you want me to do?
B5.
Okay. What's B5 about, Andek?
It's about. Hang on. I just opened the question.
Yeah. What version?
B2.
17, 18?
Yeah.
Matt, we were just saying for the significant figures, okay? Answer to 3 significant figures, calculation to 4 significant figures, and if you need to use your answer later in the question, actually use the 4 significant figures, not the 3 significant figure. Do you know what I mean? If part B requires the answer from part A, use the answer from part A in 4 significant figures. Does that make sense? Yeah. Right, you got the question, Andek? Where's Siba?
She went to GNIB.
GNIB today? What she needs to do with GNIB today?
She didn't got the target. And she needs it for re-entry inside.
That's, yeah, okay. You got it?
Yeah.
Okay, go for it.
In Rutherford's alpha particle scattering experiment, a thin beam of alpha particles of identical kinetic energies incident on thin wool foil.
Yeah.
And the resulting pattern is observed. So we get like.
Yeah, okay. And what's the question? Yeah, good, okay. And oh, they ask, this one they ask you to draw what happens, is it?
Yeah.
Yeah. So look, this is gold AU, isn't it?
Yes.
Now, what charge does the alpha particles have? Alpha particles have what charge? Do you remember? Positive. So what happens is, you have your electron going around the gold. So when the alpha particle passes near an electron, it deflects.
Shouldn't it be going in?
Oh.
It's positive.
Yeah, you're right. Sorry, thanks.
Oh, I see.
That's like a little negative, and this is positive. No. Oh yeah. I think it could get pulled like this, perhaps. Let's do the one in the middle first. That's easiest. You can bounce back, right? I thought these scatter like this. I think actually what's happening, Andek, is because the nucleus is positively charged, when it gets close to the nucleus, it scatters.
So it goes inside and then outside.
Well, in between the nucleus and the electron, I guess. Do you know what you can do? We can get this figured. We can get this sorted. Oh, my picture's terrible. If you just go to Google Images and type in Rutherford scattering, we'll get a picture. Can we go back to image results? I'm sure we can get a nicer picture. Yeah, this is kind of what I was picturing. So the ones on the outside bend a little bit, and then the one in the middle bounces off. Yeah. No, that's fine. That's what happens. Okay, what's next?
Oh, continue.
Well, yeah, to, yeah.
State one of the three conclusions. One of the three conclusions about the nature of the atom, which we learn from Rutherford's experiment.
State one of the conclusions.
One of the three.
Yeah, so basically, Rutherford did this experiment because you probably learned this in chemistry. At the time, there was different models of what the atom looks like. Did you do this in chemistry? Like one of them was called the plum pudding model. No, you haven't heard this in chemistry? Okay. So anyways, I taught you this in chemistry, but well, there was different theories of what the atom structure was. So some people thought that the electrons and protons are mixed together in like a blob, and some people thought, like Rutherford, that the electrons orbited around the protons. Okay, so this experiment was to verify that the electrons orbit around the proton. So that's one of the conclusions. So it said only state one of them.
Yeah.
So that the electrons, which are negative, orbit the nucleus, which is positive. Yeah, okay, what's next? So, Andek, when you're ready.
Give reason why the gold foil was chosen to be thin.
Yeah, basically, the simplest way to put it is that you want the particles to pass through the gold. If the gold is too thick, they'll just all stop. Okay, so you want the alpha to pass through the gold, so it can't be too thick. Because if you have too much gold, then all the particles will come backwards and you won't really know what's happening. What Rutherford, I think, was able to do, he was able to measure these angles, and from using a lot of complicated maths, he was able to work out what the structure must be. Okay, so basically it all comes down to his measurements of the angles from the scattering. You can look it up online. It's a bit complicated. You wouldn't do it at IFY level. It'd be university level. So what's next?
Give a reason why it was important that the beam of alpha particles was narrow.
Yeah, I suppose you want the beam to be as straight as possible because you want to accurately measure the scattering. So like, I'll give you an example, okay? Imagine that the alpha particles are coming out in a big fat beam like this. Then when they scatter, when they scatter, it's difficult to look at the angles because you don't know where they start. If you think that it's here, but it's really here, you get a different angle. So really it just comes down to, you want to be able to accurately measure the angles. You know, so you don't want the beam to be much wider than the atom. I don't know how they put this in the marking scheme. I guess what I would say, it is necessary to have a narrow beam which should be roughly the size of the atom, so that accurate scattering angles can be measured. Now, I would love to know what they put in as the marking scheme answers. If you have that, it would be great. Oh no, don't say but. Why did you have to say but? Go on.
3 months.
3 marks?
Yes. Just now they want
double sweet.
1 mark, and allow other sensible answers based on sound physics.
Good, okay, so they're being flexible. So as long as your answer is reasonable based on actual physics, you can get your marks. So what are other possible answers? Well, I mean, you could simply say a narrow beam allows for more control of the conditions of the experiment. You know? Like, you don't want to be sloppy. You don't want to be messy. You don't want your alpha particles going everywhere. That's a good reason too. You know? Are you okay with that one?
Yeah.
Yeah? Ken? It's okay? Are you sure? You're so quiet, I can never know if you're happy or unhappy. Okay. Did you ever speak an exam? Who was your partner? Who? Siva? That's good. How do you think you did? Bad? With Siva?
I was bad, but she was good.
I don't know. What was your topic?
Free tuition fee for national universities.
Okay. Easier or harder than the, what was yours, environmental cost of importing food? Was it? Something like this. Yeah. Do you have yours?
Yeah.
Who's your partner?
Sure.
Chow?
Yeah.
And how did you two do?
I think he spoke more than me.
Really? Okay. Alright, what's the next question?
B. The isotope goal was the isotope goal used in the foil was AU-19779.
AU-197
Yeah.
and
79.
79. Okay.
The diameter of the nucleus was found to be no more than 7 times 10 to the minus 15 meters.
7 times 10 to the minus 15 meters. Okay.
B1 is use the data provided to determine the minimum density of the gold nucleus.
Right. They want the density of the gold.
Yeah.
So look, density is mass over volume. Now we're going to need to work out the mass of the gold. Now we can work it out roughly, but I wonder, did they give you any information in the question? For example, it'd be wonderful if they gave you something like molar mass or... No? Oh, that's okay, we don't need to know it.
We only know the diameter of the nucleus.
Fine, so I don't know how strict they're going to be, but the only way I can think of doing this is the volume we can work out. It's 3.5. Sorry, let me be a little nearer. 4 over 3 pi or cubed. Now, the problem is we need to work out the mass. So we need to think carefully what we have. So this nucleus has 79 nucleons. Now, how big is a nucleon? Well, the mass of a proton and the mass of a neutron, they're about the same. They're about 1 AMU. Yeah?
Just to be clear, nucleon is mass of proton and neutron.
A nucleon just means a proton or a neutron. A thing in the nucleus.
You don't need the number up top.
What is? Oh, that's the nucleon number. But you can use nucleon as a noun to describe anything in the nucleus. So I could say, for example, a neutron is a nucleon. A proton is a nucleon. I couldn't say an electron is a nucleon because
It's on the shelf.
it's on the shell, yeah. It's okay, yeah. So you can do this two ways. You can either work out the number of protons and multiply it by the mass of a proton plus the number of neutrons times the mass of a neutron. But how many marks is it? This will give us a clue.
4.
4.
Yeah.
Oh, okay. So I think they do want us to be a bit more accurate. Because I was just going to write on the top here 79U. But I'll be a little bit more precise.
Is this the mark is in the...
Oh, don't tell me yet. Don't taint me. I want to see if I can get it right. So, how many protons do we have? Well, we have 79. And the mass of the proton is both in the formula book and on your calculator. On the calculator you should have How many neutrons do we have? 118 mass of the neutron. Both of these are in the book or the calculator.
Mass of proton.
Yeah, so can you type this in, please, for me? And we'll see what we get.
Couldn't find it.
Huh?
I couldn't find the mass of
Is it not? Can you hand me up the formula book, Matt? Can you pass that up, please? I thought it was in the book.
Yes. Maybe that's a mess.
Oh, they don't okay. They just say a U. So, yeah, okay, so actually, you can do this, you can only do this if you have the calculator.
that.
Yeah, but, yeah,
Yes.
technically it's slightly different, but because they don't have the masses in the formula book, it tells me that they're happy for you just to use a U. So, you can do this instead. 197U over 4 over 3 pi 3.5 times 10 to the minus 15. Okay. And U is in the formula book. So can you type that in?
times 10 to the power 18.
1.83. Now, okay. Actually, stop typing for a second, Andek. I want to give you something important. A little tip for the exam. Okay, a little tip. Can you give me this to 4 significant figures? Oh. Times 10 to the 18? It's fairly dense. Okay.
R is like the diameter of its tube.
Or is the radius, yeah. Now, the reason I did this is because in the exam what you should do is this. You should give the 4 significant figures and then you should round it. And the reason I recommend doing this is because later in the question, if you have more calculations to do, you should use that number later. Yeah?
The 4 significant figure is rounded up, so we make it 3
Ooh.
rounded up twice.
Oh, that would be bad. Okay, what is it? 8, 3,
4, 7.
4, 7, dot, dot, dot. Now that gets us out of that pickle. So that would be 183. Okay. Yeah, dot, dot, dot will do fine. Alright, so what is the answer in the marking scheme? Don't break my heart.
The whole answer?
Yeah,
1.83 times 10 to minus 18. Yeah.
thank you, thank you. That wasn't too bad for 4 marks. Yeah. You see, this is why I say the atom question is a good question in the exam. What's next, so?
Another nuclear has a nuclear number of 125.
Right?
Determine the maximum diameter of this nucleus. Assume its density is the same as the Bohr.
Oh, boring. So, density equals mass over volume, and they said the volume is, the density is the same. So we know the density. Yeah? We can know the mass because we have this. And what do they want? The radius? The diameter?
The maximum diameter, yeah.
Yeah, so volume is mass over density, which is 125 AMU over 1.8347 dot 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 times 10 to the 18. Okay? Wait, now the volume is 4 over 3 pi r cubed, right? So we'll get the r, we'll say this is 3 over 4 times 125u over 1.8347 dot 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 times 10 to the 18 times 1 over pi cube root. That gives me the r. I don't want the r, I want the diameter. So what do I do to this answer?
That's 2.
Times 2. See what we get. How many marks was that now, Andek? Was it
3.
6.02 times 10
now? Give me a few places. 6 point
0.1517
dot 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 times.
10 to the power minus 50.
Okay, so then in the exam you present your answer as 6.02 times 10 to the minus 15 meters. Okay. And what's the market scheme answer?
6 times 10 to the power minus
Yep, that's it.
6.00.
No, but the market is 6.00, but it's
Yeah, but this is. I think this is, yeah. So it means I would lose 1 mark here because I don't have the right digits.
oh, even the 2 is.
Oh, I might know the reason why for the difference, because I have a feeling that you use the U on the calculator, but the U in the formula book is not exactly the same because there's less digits in it.
Yeah.
Could you retype this in but with the different U? Andek, give us the value of the U in the formula book.
U is 1.66 times 10 to minus 27.
Thanks, Matt. So this is a bit annoying, of course, because it means, well, it's not a problem for you actually, because your calculator doesn't have the U on it. So you would have to type it in anyways.
6.
It's 6.
6.00.
So, Matt, as nice as the shortcuts are on the calculator, it seems like this exam writer is being very strict about using the values in the formula book, which is a pain, of course, because you can save a lot of time using the built-in values. But the reason for the difference is because the calculator, I think, has this number up to maybe like 8 places of decimal. How many places to go?
Here is 1.67.
Yeah, okay.
1.6726217777.
Oh, the formula book is 1.66. Strange. So it means that the person is being very strict. He wants you to use only the values in the formula book.
Wait, so even the size 2 is the mark off?
Yep. Yep, I'm not joking. He's very strict about this type of stuff. Okay, what's the next one? So,
Complete the following decay equations.
oh great. Oh nice, I like the decay equation, very easy. Right, what's the first one?
So alpha decay.
Yeah.
Rn
Rn
219
219
and 86.
86 decays
Yeah. PO.
huh?
PO.
B
P.
P
PO. Unknown on top and 84.
plus
Plus this is alpha, right? Yeah.
Yes.
yeah, but actually they used the wrong symbol. That's I remember. Theirs looks a bit like this, doesn't it?
Yeah.
Yeah, that's proportional. They mistyped it. The alpha symbol needs to be a bit shorter, like kind of like this. Anyway, it's no big deal. So, what's this numbers here?
4 and 2.
4 and 2. Oh, sorry, of course it is alpha, for goodness sake. Anything else?
No, that's all.
Ah, well. For babies, right? What's the number here?
215.
215. How many marks is that?
4. 1.
Right, what's the next one?
Beta minus decay.
So what do they have here?
C and 40 on top. Unknown and at the bottom.
Well, you kind of already know what, if it's C, right?
Yeah.
You already know what it's going to be.
And then it makes
It's 6, isn't it? Yeah. Hardly a mystery, but go on.
it makes N.
Which one?
N.
Capital N?
Yeah.
Oh, nitrogen, yeah, sorry, yeah.
Unknown and 7.
Okay.
And E, small e electrons.
Yeah.
So it's 0 and -1.
Yeah.
And V minus,
Like this,
and then like a minus on top.
like that.
Um,
Oh, bar on top, like
yeah,
that. Any numbers?
0, 0.
Yeah, so this guy is gamma.
Isn't this?
Yeah, I know, there's two symbols they use for gamma. It's like this, but some physics people use this symbol, which I know seems strange because it's called gamma. Why not use the letter gamma? But they decided, no, we'll use a different Greek letter. We'll use, this Greek letter is called mu, N-U, mu. Some people just want to be awkward. Now, this guy at the top, easy peasy, what is it? Is this number here? 14. And you knew this one already. 6.
6.
The
Oh, okay, yeah.
the marks is wrong.
No, don't say that. Really? They didn't know how to add here?
7.
They say carbon is 7.
They said carbon is 7. Oh, that's just outrageous. That is a disgrace. An absolute disgrace. What is that? What is 7? What's after carbon? Oh yeah, nitrogen. Oh yeah, of course, yeah. These, you know, these are the people I have to work with. This is what I have to deal with. Okay, what's the next one?
Beta plus decay,
Yeah,
which is P.
P.
P, yeah.
What's P? No.
Phosphorus.
P is phosphorus? I thought it was like P something. Just P? Okay. What's on the top?
30.
Huh?
30.
Okay.
And 15.
Okay.
Si. 30 and
Okay.
plus electron 0 and +1.
Yeah. Plus another gamma.
Yeah. No, is it gamma without the line on top?
Without the line.
Yeah.
So look, I emailed NCUK about this because I said to them, students don't study this type of decay. This is different to the beta decay in number 2. You can see what the difference is here. This -1 is now actually a +1. Now the reason for this -1 in the beta decay is because what happens is one of the protons, you get an extra proton basically. So here you began with 6 protons, and here you get 7 protons. So remember we said one of the neutrons turned into a proton. So that -1 there is to represent a proton becoming a neutron.
So it's an alpha. Beta minus decay, that's why it's.
That's beta minus decay, it's called beta minus decay. We just called it beta decay because we don't study beta plus decay, so there was no need for us to say plus or minus. Now what do you think is happening here? You have a 1,
So it's 14.
so this should be 14. Yeah, so how would you describe the beta decay, a positive beta decay? One of the protons becomes a neutron, is the opposite. Now, it's no big deal because you can still balance this, right? But I just said in an email to them this week, do students need to know this because it's not on the syllabus? And they said, no. They didn't exactly give me a definite answer. But you don't really need to know this because you can still balance the equation anyways. It's no big deal. Right, so what was it, 3 marks for that?
4.
So which one had 2?
For the beta minus decay, 2 is.
What? This one was 2,
Yeah.
and this was 1 and 1.
Yeah.
Why?
Because you have 2 values.
Oh! Okay. But it was hardly twice the work. You know? Alright. What's next?
Meaning 2 quantities which are always conserved in nuclear reaction.
Yeah, and this is another thing I emailed NCUK about because we were talking about this because they referenced things that weren't on the syllabus. Anyways, in the lesson I gave you 4 things which are conserved. You only have to name 2 of them. So one thing which is conserved is momentum. Another thing which is conserved is charge. Okay. Another thing which is conserved is the total nucleon number. And also energy is conserved, as long as you remember that mass is a form of energy as well. So you just need to pick 2 of those, and that's fine. How many marks for that? Probably 2, right? Yeah. Right, what's next?
That's all.
That was the section B, atoms question.
Yeah.
Now you see, guys, do you see why I'm saying you should do the atoms question? It's not particularly challenging.
But the first few questions,
I just did blah 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 a little bit. No, you don't like blah blah blah? Okay. Fine. Alright, whenever you're ready, we can look at whatever you want to next.
Can you do B4?
What's B4 about?
B4 is wave. The triple tank.
Oh yeah, okay. Right. How's it start?
2 waves in a ripple tank meet at a point. One wave has an amplitude of 5 millimeters. The other wave has an amplitude of 3 millimeters.
Are you sure we didn't do this? This seems very familiar.
We didn't finish this.
We didn't finish it.
Yeah.
Fine, okay. So, the first question was, what is the...
Maximum.
Yeah, so if one wave has an amplitude of 5, is it?
Yeah.
And the other one has an amplitude of 3, what's the maximum possible amplitude when you combine these waves?
8.
It's 8 millimeters. 1 mark?
Yeah.
Okay, next. Oh, let me guess. What's the minimum?
Yeah.
Yeah, okay. So what's the minimum?
2.
2. Okay. Next.
Give the name of the process by which the waves are added.
Do you remember? Superposition. Okay.
So this is B. 2 coherent sources of waves X and Y are arranged 15 centimeters apart in a ripple tank.
Right, so hang on. That 15 centimeters apart represents the D. Okay. Yeah, so that's the small d. Oh wait, let me just see. And that one is 0.8. Okay, continue. You can keep reading, yeah. After the 15 centimeters.
Okay. In a ripple tank and the resulting fringe pattern is observed.
Yeah.
One is what is meant by coherent.
So coherent, we said, are 2 waves in phase with the same wavelength. Now, I don't know if you have to say with the same wavelength. In the marking scheme, do they say you have to say that?
same frequency and constant phase difference.
Constant phase difference is the same meaning as in phase. That's what that means. But you said same frequency. Now, if they're both moving at the same speed, their wavelengths will be the same if their frequencies are the same. Okay, I'm going to... I'm not happy. I don't know if I want to switch this to frequency. I know in the marking scheme they said frequency, but do you have your phone handy, Kim? Could you just Google definition coherent waves? I just want to see what you get. Yeah.
If in physics two wave sources are perfectly coherent, if they have a constant phase difference and the same frequency.
Same frequency, okay. Alright, fine, not same wavelength. Thank you. Alright. What's next?
Maxima and minima are observed along the line shown. Sketch the pattern of the amplitude you might expect to see along this line.
Yeah, okay, so what happens is here you get a fringe here, and then a fringe here, and then a fringe here, and a fringe here, and then a fringe here. And the reason is the wave here has the most amplitude. It's the brightest, or the loudest, or whatever. And then here is another crest, but it's not as bright, it's not as loud, its amplitude is not as big. So if you were to kind of look here, that is not an eye. If you were to look at the wave here, what you'd see is it's kind of flat, there's a little peak here, there's a bigger peak here, there's a bigger peak here, and then another peak here, and then back down again. That's what the wave would look like as it hits the surface.
Smooth, sinusoidal.
That is what I drew. It's smooth. So in other words, they don't want you to do this. And that word, have you seen that word before? Sinusoidal.
No.
It. What word is it like in maths? Is there any word like this in maths? There is. Look at the beginning of it. Look at the first few letters.
Maxima and minima.
No, for sinusoidal. Sine. So, sinusoidal is the adjective for sine. So, saying something is sinusoidal means you're saying it looks like a sine. Yeah. Okay, what's next?
Do we have to draw the eye?
No.
Okay.
You don't need to draw the eye of Sauron.
Explain using the concept of path difference how maxima and minima form.
Yeah, so look, what happens here is the reason you get a maximum here is when the waves combine, what happens is two crests meet. That's what happens. And the reason why this is so low is what happens is when the waves combine, let's say this is a crest, this is at a crest, and then maybe another wave comes in at a trough, and the crest and the trough combine and they shrink it. Now, the reason for that is, if I have one wave, look, there's one wavelength, there's two wavelengths. Here's another wave. I'll start at the top. So, can you see that this crest meets with this trough, so they cancel. And if you kind of visualize this, there's the crest there, there's the crest there. There's a difference between the two crests. How big is that difference? That distance is half a wavelength. So what's happening is when there is a dark spot, it's because the two waves have a path difference of half a wavelength. When there's a bright spot, the two waves meet together with no path difference, and the crest combine. So you would just say when the path difference equals 0, that produces a large amplitude. But when the path difference equals half a wavelength, that produces a minimum amplitude. that, did they have something similar in the marking scheme? How many marks was that?
4.
4. Oh, I might have to write more. What did they say in the marking scheme?
There's a difference in path length from sources x and y to a point on the line.
Yeah.
And at some points, waves from x and y arrive in phase.
Yeah.
Producing constructive interference and order maximum.
Good, so that's that one.
And some points, waves from x and y arrive anti-phase, producing destructive interference and or minimum.
So they used a new term which I thought was interesting. I've not seen it before in the exam. You don't have to use it, but they called this situation an antiphase. Is that what you said?
Yeah.
It's interesting. Okay. Right, what's next now? Oh, when you're ready.
The perpendicular distance from the line joining x and y to the line of observation is 8 centimeters. Determine the wavelength which could produce a fringe width of 10 centimeters.
Okay, so you have to use the formula x equals lambda d over d. You said the x is 10 centimeters. The lambda we said is 80 centimeters, and what did we say the d was? 15 centimeters. Do I have all that right?
The fringe width is 10 centimeters.
Yeah.
And the line joining x and y is 80 centimeters.
Yeah. And they want the wavelength, isn't it?
Yeah.
All right. So what do you get here?
Zero.
0.0188. Any did you round that? Eight, 7, 5. Thank you. Right. What's next?
Describe the effect on the fringe width of reducing the wavelength by a factor of 4.
Boring. Right. What happens to x if you divide the lambda by 4? Is that what they're asking for?
Yeah.
So, what happens?
Divide by 4.
Yeah. Right, next.
The answer wants us to calculate it, so 10 over 4.
Oh.
Yeah.
Oh. What was the x? It was 0.1.
Yeah.
They want the new x.
Yeah.
Oh, so it's just that divided by 4, isn't it? So what's that? 0.025 meters. Yeah? Okay, what's next?
Let's see. Light from a monochromatic source is incident normally onto a diffraction grating with 1000 lines per millimeters. The light passes through the grating and forms a pattern on the screen which plays the other side. So, M1 is shown that the spacing of the lines is 1.
Okay, so
1 millimeter.
that's just 1 over 1000 millimeters. So that's 1 over 10 to the... Sorry, I did that wrong. That's 1 millimeter over 1000. So that's 10 to the minus 6 meters.
Yeah.
Okay, what's next?
So what is this? What is this unit?
Oh, did they write us 1 micro?
Micro.
Yeah, okay. Next.
The first bright maximum visible occurs at 25 degrees to the normal. Determine the wavelength of the light.
Okay, so n lambda equals d sine theta. Alright, so what's that? What's sine 25? Just give me the sine 25.
0.4226.
Right, so if I make that nano,
That is by 9.
yeah, so that would be 423 nanometers. Okie dokie. Next. You don't have to convert it, I just like to, it's nice. What's next now?
How many maxima are visible in total from this arrangement?
Okay, so that's using the formula n lambda equals d sine theta. But sine theta, the biggest it could ever be is 1, right? In fact, you could never get 1 here because that would mean theta is 90 and it wouldn't actually hit the wall. So you can say that n lambda is always less than d. So that means the n will be less than d over lambda. And that d over lambda is 10 to the minus 6 over... Now you see, this is a good example of what I mean. We should use this number as a calculation. 0.4226 times 10 to the minus 6. They cancel. So n should be less than 1 over 0.4226. Which is, what's that, 2.5 or something?
2.37.
So what is the biggest n could be? Could be big. The biggest could be is 2, and so is the question what's the biggest value of n, or what's the number of fringes, or
How many maxima are
yeah, okay, so or would it be 5? Because you have to count 0. Because what you have is minus 2, minus 1, 0, 1, 2. Maximum here, 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 and here. So I'd say the answer is 5. Yeah? Okay.
This formula is not correct.
Yeah, correct. It might be in the one for this year.
change as well?
They only ever add formulas, they never take it out. I thought they put this one in. But you don't need to know it, Matt, because you can always just do it using maths trigonometry. If you draw the triangle, use the formula for x. Oh no, actually, no, you do need this formula for this one. Yeah, alright. Yeah, you need to know it. Right, what's next?
That's it.
That's it? That was alright. That was alright. See, it always breaks my heart that students don't do as well as I think they should, because the questions aren't that bad. Like, a little part of me inside dies a little bit when I start correcting your exams. It always breaks my heart that you do better in chemistry than physics. Breaks my heart. Yeah. Why does this happen? I don't know. I don't know. I think it's because Lorraine really, she punishes you to work hard. No? Right, go on, what's your question?
V3.
Version 3. Okay. What year?
17, 18.
Okay. Can you guys open that? 1718 version 3. Right, which one?
Question 85.
Okay.
A wire of length 2 meters carries a current of 4 ampere, 4 amp horizontally from east to west.
You can say ampere, that's fine.
In the horizontal magnetic field of 6 times 10 to the minus 3.
Oh, hang on now, I have to picture this. It goes from east to west.
So it's the
And they said there's a horizontal field, but they didn't say which direction yet. Go on.
In the horizontal magnetic field of 6 times 10 to the minus 3 Tesla directed from south to north.
Okay. And what you said it was 6 times 10 to the
-3.
million Tesla. Okay, and this is
east to west, so it's the other way around.
was it east to west?
East to west.
Oh, sorry. So it's like that. Okay. 4 amps. Okay.
A1. In which direction is the resulting magnetic force on the wire?
Left-hand rule. Right. Watch. Look. Need to look at my left hand here. The B is north. Okay.
That's the field.
The field. Yeah. The I, the current, is left.
So it's going to be west, I think.
Yeah. So the answer is F is into the page.
A2. Determine the magnitude of the magnetic force on wire.
That's the formula, Bill. Is that 48 times 10 to the minus 3 newtons?
-2.
Yes.
Oh yes, it's 48 millinewtons. Okay.
B. A current carrying wire creates a magnetic field. Sketch the magnetic field produced by wire if the current is flowing perpendicularly into the page.
Right. Now you see, this is why I had you do all those drawings in your notebook, okay? Because you get these in the exam. So the current is going into the page. The current is going into the page. So which rule is this? This is the right hand grip rule, where if you have a current, you put your right hand around the current so that your thumb is in the direction of the current, and the magnetic field is the way your fingers curve. So if you visualize that, it means you'll have a magnetic field going around it like this.
This is always right.
Yes, right hand grip rule, yeah.
This is
You've got your right hand grip, your left hand Fleming, and your right hand Fleming. 3 hand rules. Super. Right, what's next?
A6.
Oh, another question. Right, so what was the problem with this one, Matt? We didn't like it. The sketch, okay. A6.
A small pinhole in a piece of metal foil produces a diffraction pattern when various light sources are incident upon it.
Okay.
A. Describe the effect on the diffraction pattern of making the pinhole in the foil larger.
Right, so you might remember this diagram we had in the lessons. You get a large diffraction when it's a small hole, and if you make the hole bigger, the diffraction is less. So the answer is less diffraction. Do you remember that picture from the slides? Do you know the one I'm talking about? Yeah. Okay, what's next?
The width of the central fringe of the diffraction pattern for monochromatic red light is measured. Describe the effect on the width of using a monochromatic blue light source instead.
Interesting. Okay, so look, you have the formula x equals lambda d over d, right? The only thing they change is the light, which means they change the lambda. Now, what happened, Matt? You said it went from red to blue, is it?
Yes.
Red to blue means, let me think. It means you're increasing the frequency, which means you're decreasing the wavelength, which means the x should be less.
How do you know if it's an increase or decrease?
Yeah, it's the colours of the rainbow. So it goes from low frequency to high frequency along the rainbow colours. Red, orange, yellow, green, blue, indigo, violet. So, less as well. Okay, what's next?
Describe what you would expect to see if a
Oh,
strong,
this describing. Right, go on. Describe what you'd expect to see if...
a strong white light source was
Right, we'd expect to see a rainbow. We did this question in class. Yeah.
The answer says spectrum other fringes.
Oh, okay, sorry, I'm not being technical enough when I say rainbow. But yes, a spectrum of all the colours, i.e. a rainbow of colours.
Yeah, let's just discuss.
BV3.
If there's a small pinhole, if you shine like white lights, it's rainbow.
Yes, now a couple of things. It would have to be a very small pinhole, and your white light needs to be proper white light, and the only really source of that is the sun. So what you would have to do is you'd have to get this room completely dark, put a black screen up on the window, and put a tiny pinhole in it. Then the little bit of light that comes in and hits the desk here, that would be a little circle of a rainbow colour.
So how does it work in the sky?
So what happens is when it passes through a raindrop, a little raindrop, it diffracts out into all the colours. So the raindrop acts like the pinhole. Okay. Right, what's next now?
A7.
A7. Well, no, actually, sorry, this is math. Is there more to this A6? You didn't like it? Too much describing. Yeah. Right. No, we need to focus. Like, if you want to do A7, that's fine, but, I mean, I want you to look at what you tried to see where you got stuck. So, were these the only ones you got stuck on?
A7.
Okay. You got stuck on A7?
Not really stuck, but I want to know the answer.
Okay. What's the question?
The A1, they find the term binding energy per
Binding
nucleon.
energy per nucleon. So this is the energy required per nucleon in the nucleus to hold it together, i.e. to overcome the repulsion of protons, i.e. this is the energy due to strong nuclear force. Now I probably wrote way too much there.
The Marquis says energy quite separate and nucleosity is constituted nucleons divided by total number of nucleons.
That's another definition, because you can think of the binding energy as the energy required to keep the atom together. It's also the energy required to break the atom. It's the same number. So either definition will be fine.
Separate or binding will be fine.
Yeah, so your other choices here is the energy required per nucleon in the nucleus to, and instead of saying hold it together, you could write separate it. So instead of writing hold it together, you could write to split it. It's the same thing, for example, if I say there's 5 joules of energy required to stick these together, then it's also true to say there are 5 joules of energy required to pull them apart. It's a symmetric thing. Right, what's next, Matt?
The binding energy of nucleus of lead 206 is 16.
1 sec, sorry, lead 206 is
1622.27 mega.
1622.27
mega electrons volt. Determine the binding energy per nucleon for lead 206.
or in just divide by 206. This is the total binding energy, and they ask for the binding energy per nucleon.
Yes.
Oh, divide by 206.
B. Describe the process of induced nuclear fission.
Right, so fusion is when, spell it,
Fusion, fission.
Fission. Yeah? Yeah, so this is when one heavy isotope is split into two or more lighter isotopes, releasing a vast amount of energy. Vast meaning a huge amount of energy. So you take one heavy isotope, split it into two or more lighter isotopes, and you get lots of energy in the process. That is fission. Is the next one going to be fusion?
That's a problem on piece.
Okay. So what was the problem with that one, Matt? The word induced is a bit redundant. You don't have to say it.
It's kind of reaction.
Yeah, I suppose induced just means it's artificial. So often you break the atom by smashing a neutron with it. So if you want, this is the definition of fission, and the only really meaning of the word induced here is usually something like normally the fission is done via collision with a neutron. Because you can have induced fission, which is when you do it in a power plant, but you also have naturally occurring fission, where you would just have a piece of uranium and it would just break into smaller pieces, you know. I think that another word you could use instead of induced perhaps is, I don't know, controlled or something like this. Right, what else do we need to see?
Briefly describe A8.
A8?
Yeah.
Okay. You really don't like describing questions, that's all I'm here. What's A8?
A transformer is used to reduce the voltage supply to a house from 3,000 volts to 240 volts.
Yeah?
A. Briefly describe the construction of a step-down transformer.
Okay, so a picture is good here, Matt. You got your iron core, you've got your primary coil, and you got your secondary coil with less turns
It's always like that.
for a step down transformer. Yeah. So a primary coil is wrapped. Is wrapped 1p or 2?
2 piece.
2p's. Wrapped around the left, wrapped around one end of an iron core as shown. A secondary coil is wrapped around the other end as shown.
We have to draw.
I think it would be good.
Maybe it's explain like laser red.
I don't get it. Just give me a second. Right, so I was about to put in red. The number of turns on the secondary is less than the number of turns on the primary. And then you have to say and this is important also, Matt, AC current is passed through the primary, inducing a lower voltage current in the secondary. Now, I know they said describe briefly, but I can't think of how you could describe it any briefer than that.
Hall with primary and secondary points and greater number of terms on primary
Yeah.
and secondary.
Yeah, but you see, that's not a full answer because it's important that you use AC. Because the transformer doesn't work if you use DC. It doesn't.
What is AC?
Alternating current. Okie dokie. Right, we'll have to wrap it up there because I have a meeting with Connell now shortly. And then I have another class. I have to meet with Connell to discuss a meeting we're going to have next week. My meetings now have meetings. I have to have a meeting about the meetings. This is life. And then we'll probably have to have a meeting after the meeting next week. Madness. Madness. Right, before you go, just a couple of